In this section, we're going to look at how to diagram electric fields. So this is called visualizing the electric field. Most of this is actually going to be sketches. To start with, we'll talk about what the electric field is. We'll look at the equation for the electric field, but then we'll spend the rest of the time talking about how to diagram an electric field. So as we've talked about, most forces that we did in mechanics were all contact forces, like tension or normal force or friction. There had to be two things touching in order for a force to be there. Gravitational force, electric force, and actually magnetism as well also has a force that acts at a distance, so nothing has to be touching. So in order to kind of understand why forces act the way that they do, scientists came up with the idea of a field. A field isn't actually a physical thing, but it's more of just a concept that can really tell us how forces act, when they're stronger, when they're weaker, that sort of a thing. So electric field force, the strength depends on how much charge you have. The more charge you have, the stronger it is, and the distance between the charges that you're looking at. With an increased distance, you have a weaker electric field for the most part. We'll look at some examples on that. So if you have an electric field, anytime you have a charged object, in theory, that electric field extends for infinity, just like the gravitational force extends for infinity. We talked about a dust bunny here and a dust bunny, in China, would actually have a gravitational force on each other, but because of the large distance between the two and their small mass, that force is insignificant. The same thing happens with electric charges. So if you have two electric charges that are small charges with a great distance between them, then that force is next to nothing, is not necessary to deal with. The same thing happens. So that's our electric field. That's what we're going to be looking at. Here's the equation that goes with electric field strength. We probably won't do much with that given the amount of time that we have left in the school year, but you can see how that lines up with the Coulomb's law that we looked at before, where you also have Coulomb's constant. That's the subscript C here is just for constant, a general term constant with a K, and the subscript Coulomb, subscript C for Coulomb, so don't worry about that. And then the charge over the distance squared. So that's the formula that goes with it, but again, we're going to spend most of this talking about how to diagram electric fields. So a couple more things about electric fields. So we said that's the region near a charge where you can have a force on a test charge. The test charge is something that, again, is another thing that's an idea. A test charge is, we're always going to put a positive test charge in a field, and the positive test charge will define the direction of the electric field. So they call it a test charge because you don't want to put a charge that would actually affect the field itself. So we don't want it to become part of an electric field. We just determine the direction of an electric field by what direction would a positive test charge move if it were in there. So that's what they mean by that. A couple more rules to do with electric field lines. These will make more sense when we see the pictures that are coming up. One is that the field lines are tangent to the electric force. I'll give you an example of that on a picture. So that gives you the direction of the electric force. It doesn't mean that a charge would necessarily follow a field line, but it would give the direction of the force on it at any time or any point. Another rule is that the field lines leave the charged object in the direction perpendicular to the object. Again, I'll show you that on the diagram. And the last one is that field lines won't cross each other. If you've seen lines of, for magnets, when you do like little iron filing thing and you can see lines of force on magnets, you see the same kind of pictures here for electric fields. So you might be more familiar with that from middle school or whenever you did that last. So for gravity, that kind of got cut off just a little bit. I don't think I can move it. Oh, I can move it. For gravity, in this chapter, you're going to notice that they do a lot of analogies with gravity, again, because you're more familiar with gravity and you've studied it recently and that sort of thing. So we're going to take a look at how you would diagram gravitational field lines and then make an analogy with what you would do for electric field lines. So think about this. If you're on the Earth's surface, you could, if you were to put a mass above the Earth's surface, that mass would be drawn to the surface of the Earth because of its gravitational field. So you would have a gravitational field that looks something like this. The parallel lines are indicating that they are perpendicular to the surface here, and then the direction determined by the direction that a mass would fall. Okay, notice the lines never cross each other. That was one of the rules as well. If I were to again do another field strength for the moon that has a weaker gravitational field, I diagram that by changing the spacing of the lines. So having a weaker gravitational acceleration or gravitational field strength, I'm going to have fewer lines. And if I were to do this on Jupiter, Jupiter has a very strong field strength. So I'm going to diagram that with a lot of lines. So these are qualitative in that the number of lines is irrelevant. The number of lines only matters when you're comparing it to something else like these three. Oh, and Jupiter got cut off a little bit there. Can't make my screen any bigger. There's the Jupiter part. So we're going to do the same thing with these three objects, except we're going to zoom way out. So if you zoom far away from the planet and you looked at Earth, Earth would be a sphere then, right? If you zoom out. So I'm going to do the same thing. I'm going to have a test mass for the moon and Jupiter as well. And if I do this, if I had a test mass for the Earth and I put it anywhere around the Earth, that mass would be drawn to the Earth. And so that would be the direction of my field is towards the Earth. And now if I wanted to represent the moon's surface having a weaker gravitational field, I would use fewer lines. And for Jupiter, I would use a lot of lines to show a stronger gravitational field. One thing to notice here is that as you move away from the Earth, the spacing between the lines increases, since we're talking about something going in a circle. That is a nice representation of the fact that the actual gravitational field strength gets weaker as you move away. Okay, the same thing for anything that's basically a sphere or a circle as we see here. Okay, so if we do the same thing here for electricity, we're going to do this with charges instead of with mass. This is the analogy to the surface of the planet for the first ones that we did, is if we had two charged plates. So we have a positive plate and a negative plate. So there's my plates, and I'm going to put a positive test mass in there. That one's kind of gigantic. Again, the test mass isn't supposed to become part of the field, just to determine the direction of the field. By the way, when you do these diagrams, you don't always have to draw a test charge on there. I just do that for these initial ones where we're learning how to do it. So you can leave that off of your own diagram, but you would see that if you put a positive charge in that field, that it would move towards the negative plate. So in this case, it's down. Now, if I had flipped the plates, if I had the negative one on top and the positive one on the bottom, then my field would be going up instead. Okay, again, if I did this diagram again with only half as many charges on each plate, then I would have fewer gravitational field lines to show that it's weaker. If I did it with more charges on each plate, then I would have more lines to show that it's more dense. Sometimes you'll see them, people get all fancy and diagram around the outside, and then they start getting curves involved. You can do that if you want to. I'm not too worried about that. I'm more worried about what's in the middle of the field with these, with the lines in the middle. So in this case, as you continue from space to space, here I have a constant field strength because the spacing of the lines here doesn't actually change within this situation. That's different if I go back and do one of the spheres. On this one I did a negative and a positive. My bar in the middle is supposed to show that these two are not interacting. Okay, so these are not in the same space, but I'm doing them on the same screen. So if I have a sphere for the negative one, if I put a positive test charge, then I know that my field is going to be pointing towards the negative. If I do the same thing with the positive sphere, I'm going to have a positive test charge is going to move away from it, so I have lines moving away. If I did the same situation where I had two negative charges, I would add more lines to show a stronger field. Same thing for the positive. Okay, so we can have a field for something that's individual like this, or we can actually do these where they're both together. So here I have the plus and the minus in the same space where they're actually going to interact. And we'll talk about some of those rules I mentioned before we started diagramming on this particular one. I think is a good one to show some of these on. So if I do a positive test charge, you can tell it's going to move towards the negative charge. So, and I put a couple positive test charge, I'm not sure why. So here I have a field line going from positive to negative. Notice this one I have leaving this plus charge perpendicular and landing perpendicular onto the negative one. Okay, now if I have one that's further down, my line's not perfect here, but if it were leaving the plus charge perpendicular, again it would land perpendicular on the negative. Now since these are spheres or circles, looks like circles since they appear flat, it's different than when we did the bars, everything was perpendicular, right? So here If I leave perpendicular, I'm going to have some bend in the middle to land perpendicular onto the negative surface. So that's how you end up with some curves. And this is one where this probably looks like some magnetism drawings that you've seen before. And I drew a whole bunch, and I even have a couple on the outside. In theory, if they extended far enough, they would wrap around and meet meet the one on the other side, but you can kind of show them coming and going that way. So again, I have, the field all the way around on the outside. On both of them, I have things being perpendicular to the sphere itself. You notice that none of the lines cross. That was one of the rules. And the last thing was that if you wanted to describe the force on something in a particular place, the force would be tangent to the line. What that means is if I put a dot like right here, I would have a force that is tangent to the line at that point. That doesn't necessarily mean a charged object would follow the line all the way to the negative. It doesn't give you the path of an object. It gives you instead just the force at that particular point. So depending on whether it was moving before, its speed, the size of its charge, all of those things, it doesn't mean it would actually follow that path, but it does give you the direction of the force. And I think those were all the rules that we mentioned before. I didn't give you one here where that had two of the same charge. I wanted to let you figure that out, but they would be repelling, so you wouldn't have lines that actually connect from one to the other. So I'll let you give those a shot on the homework. So on the homework that goes with this, you'll just be doing some diagramming, and then there's a few questions at the end to answer on this with the concepts. And that's it for drawing electric fields. I think for the most part it's pretty straightforward. Doing the homework that goes with this will probably take you about half the time of watching this video, so it shouldn't be too bad for you.